let's take attendance. 2. All right, Nick, Jamali, Cameron, Robert, Derek, Jamari, Jonah, Eric. Did he come? I don't think he came in today. Marcus, Austin, Ezra, Brian was here. Yeshua, Seth, Ben. Here. Oh, sorry. John, Mikhail, Justin, Prez, Will, Dylan, Josh. Okay, John, Molly. Okay, Dylan was here. Josh here. Omar was here. TJ. And I'll get you in the morning class. Anyone else I missed? Khalik, I'll get you in the morning class. Brian, I got. Paul, okay, I'll get you all in the morning class. Yeah, I got you. Okay, cool. Will. All right, cool. Big day today, kind of packed. We're going to be doing sorting algorithms. So again, the main reason why we're learning algorithms, later on in the real world, if you needed to sort an array, there would be a function you can call that will sort the array very optimally. But the reason why we're learning algorithms is because it's a way of thinking. A big part of computer science is like building good habits and building a different way of thinking. Oftentimes a way that you haven't learned about before, especially when we're doing all these design problems and building games and putting it into pseudocode. That's like a very different style of thinking that really you'll just develop with practice. And so sorting algorithms fall under that chain, where we're going to look at 2 different ways to sort an array. We're going to first start with selection sort, and then we're going to go into bubble sort. Any questions on anything before we get started? Okay, so before we do that, we have to recap how to swap elements, because when we sort the array, we're going to be moving around elements in the array. So in this code, we have 2 int variables, int a equals 5, b equals 3. We try to swap them with a equals b, b equals a. What's the error in this code? Yeah, so a is going to be equal to 3. But then when we try to set b equal to 5, it's going to take the current value of a, which is 3. So both values are going to end up with 3. This was when we did the example outside in class with the note card. It's like trying to toss 2 note cards at each other at the same time. It doesn't work in computer science. So in groups, I'm going to have you all write some code that's essentially going to finish the rest of this function. We have a equals 5, b equals 3, and we want to swap them. Think back to that example we did outside of class. How can you get it to stay? We'll have you 3 go together here. Robert and Jonah. Alright, we'll have you 3 together here. Again, we're trying to write code that is going to swap the values of a and b. Write down your solutions on the paper so I can check it. So yeah, temp equal A, so we're gonna create a temp variable A, and then how can we do the swaps? Cool. And what is B gonna be equal to there? Cool. You guys got it here. Cool. I think people are on the right track. So essentially when we did it outside, we realized we couldn't throw the papers to each other, so people would set one of the note cards down on the ground. That's essentially storing it in a temp variable. So int temp is equal to the value of A. So what's the value of temp going to be right now? 5. Then we can do the swap. So A is equal to B. So A is going to now be equal to 3. And what is B? Oh, I gave it away. What is B going to be equal to? Temp. Because we said temp was 5. So now this line is going to make A equal to 3. B is going to be equal to 5. Okay? Questions here? Okay. If we were to do this with arrays, so if we had an array of ints, let's say just had the values 3 and 5 right now, it will look very similar. Temp is equal to nums of 0. Do the swap, nums of 0 is equal to nums of 1, and then nums of 1 is temp. So in this case, nums of 0, this 3 is going to change to a 5, and then this 5 is going to change to a 3, and we're swapping the two elements. Yeah? Cool. So when we write pseudocode for these sorting algorithms, and I say like swap the elements at index 0 and index 1, that's essentially doing these 3 lines of code right here. Yep. All right. Cool. So let's get into the actual sorting algorithms. Can I get 5 volunteers, please, to come on up? 5 volunteers coming up. Thank you, Kadir. 4 more. Thank you, Bleak. 3 more. Thank you. You good? Okay, both of you guys can come out. Christian, thank you. Okay, so they're going to be representing our array. Hold up your numbers. Okay. And then let's have you all slide down a little bit so that I can also put something up on the screen. Okay. Actually, we don't need that for now. Okay, cool. So we have these 5 numbers. We're going to be starting from the left. So index 0 is on the left. And we want to sort the array in ascending order. If we were to just think about this in terms of English, how would we do it?
Smallest to largest.
Yeah, so essentially we want to figure out what the smallest number is. What's the smallest number here? 1. So we could have Kadir and Paul switch spots. So we'll have you guys switch. So essentially a swap right here. So now we know at this like target position, this is already set. How would we, what would essentially be the next step?
Find the second smallest.
Find the second smallest number. But instead of saying like find the second smallest, find the third smallest, find the fourth smallest, let's just say like we know Kadir is set. So now we can just assume the array is only 4 elements long. And in these 4 elements, what is the smallest number? 3. So we would swap 3 to the start of this mini array. So we'll have you two swap. And now the array we care about are just these last 3 elements. Because we know these 2 elements are already sorted. So we don't have to worry about them anymore. So out of the last 3 elements, now what is the smallest value?
5.
So then we have swapped the 5 and the 54. Now our array is just 2 elements long. This is the target position we're trying to fix. And in this case, what's the smallest value between them? 22, so we don't have to actually change anything. And then we come to the end and we're trying to fix this spot. And if there's only one thing in the array, no swaps are needed. So the way we set it up, if you guys can shuffle again one more time. We essentially have a target index that we're trying to essentially set the correct value to. So our first target index is this value 0. We're trying to see like what number in this entire array needs to go into index 0. And we figured out it would be the value of 1. So we're essentially swapping like nums of 0, if the name of this array is nums, we're swapping nums of 0 with nums of 2. So they swapped, so we'll do that swap now. So they've switched places. And now our target index that we're trying to set the correct value to is 1. And we no longer want to check anything before the target index. We want to see the smallest number after the target index. Why do we not want to check the 1 anymore?
Because the one's point places.
Yeah, like if we check the 1, then we would make them swap places. So once we have the target index, we only check elements beyond that, right? So then in the 54, we would check, is 54 less than 22, or is 50, sorry, we do like, is 22 less than 54? Yes, so our new like min value is 22. Then we check, is 5 less than 22? Yes, so our min value is now 5. Then we check, is 3 less than 5? Yes, so our min value is 3. And we figured out our min value is 3, and now it's swapped. Okay? Any questions on the algorithm? Okay, thanks for the help. We'll write out the pseudocode for this. Thank you. Okay, so if we were to write the pseudocode, oops. Okay, so there are some variables that we need. We need like we need some way to keep track of what the min value is. And we also need a way to keep track of what the min index is. That way we know which elements we're going to be swapping. Okay? So the first thing we had in our outer for loop was essentially each time we were trying to set one number in the array. So this outer for loop is going to essentially be for every element in the array. Yeah, for maybe every position in the array. This is the number we're going to be setting. And then within that, we need something for every element in the array to figure out what the smallest remaining value is. Find the smallest element remaining in the array. Okay? So this for loop is trying to check what the smallest element is in the array. And then after we find it, what do we want to do after we find the smallest element in the array? Set it, or what's the word? Kind of, what were they doing when they were changing positions?
Swap.
Yeah, so swap essentially smallest element with the target element. Okay, so if we were to do this in terms of code, everyone can see this code all right? Okay, so we have a function. I'll explain why it's a void at the end. Name selection sort, and it takes how many parameters? 2. One is the array, and one is the size of the array. Okay, so in here, we said we would create this double min value, and we would also have a min index. And in our outer for loop, we would have the target index. So this is trying to figure out each index in the array. We're trying to get the correct value. So target index is equal to 0. Target index is less than what? If we're trying to go through every element in the array or every position. In this example, it was 5. We'll use this variable size, which gives us the size of the array. And then target index plus plus. Again, this for loop syntax, you'll use a bunch with arrays. And then in here, we want to find, the goal is to find the smallest remaining value. So we can have int index. And this is where it's going to be different. Normally, we always start index off at 0. Can anyone guess what we actually wanted to start off in this algorithm? Not size, because then that would be the end of the array. Notice after we locked in one position, where did we start looking after that? Yeah, we started looking at like the next position 1, essentially the next target index we were trying to fix. Then after we figured that out, then we said the array is only 3 long. So we started at a new index. So what is index starting at? So the first time starts at 0, then it starts at 1. It's essentially based on the target index. So the target index is the position we're trying to fix. The first time we're trying to figure out what goes in position 0. So we search the entire array starting at 0. Once position 0 is fixed, our target num is 1, and we're trying to figure out what goes in element 1 of the array. So we only want to search from 1 onwards. We don't want to search anything we did before. Does that make sense? Questions here? I see some confused faces. Maybe also if we drew it out, like we figured out after the first pass that the number 1 went here. And then if everything else was like random, if we had like 54, 22, 3, 8. The next thing we're trying to do, so in our outer loop, we're trying to fix what goes in target index 1. So we're trying to see what 54 needs to swap with. Which means in the inner loop, we only want to start from 54 onwards. We don't want to check the 1 that we already locked. Does that make sense? Or can people put into questions maybe where it's confusing? Once we figure out like the 3 switches with the 54, then our target index becomes 2, because this is now the new position that we're trying to fix. And so then we want to start index here and check, is this okay, is this okay, or is this okay? Okay. So that's why the inner loop is going to be starting at target index, because we're trying to find the smallest like remaining value. I think this is the key word here. The smallest remaining value in the array. Okay? And then index is less than size, index plus plus. Okay. So here we need to do some sort of if statement. How did we figure out, in this example here, we'll switch it back. So again, we'll assume this 1 is already locked. We're trying to figure out what number goes in this target index of 1. We say that essentially before this loop runs, we're going to have min value equal to nums of target index, and min index equal to target index. So when we're trying to figure out what goes into position 1, we're going to have some variables. We're going to have min value. What is the min value? And then we're also going to have target index and min index. So min index is 1, target index is 1. What is min value? Min value nums of, what is this saying? When target index is 1, min value is equal to nums of 1. All right, do people follow that, the indexing? Yeah. Like min value is equal to the item at target index 1.
It wouldn't run at 0 first?
I guess we're assuming we already locked it,
Okay, my bad.
and now we're doing like the next one, just to show the array's getting smaller. So we're assuming we already did it for target index 0, now we're doing the next iteration of the loop, when target index is 1. Okay? So then we're trying to check, is 22 less than 54? Yes. So essentially, like in this if statement, we're trying to check if whatever the current value is, so if nums of index is less than the min value, we're going to do something, and we'll figure out what that is. So if 22 is less than 54, what do we want to change min value to?
22.
Yeah, so we want to change this to 22. And so in our code, it would look like min value is equal to what? Nums of index, because that's the element we're currently checking. And then min index is going to be equal to what? So before we were saying the smallest number was at index 1. Now we're saying the smallest value, 22, is at index 2. Or essentially just index, because we're checking every index right now. Okay, cool. Then when index increases to 3, so we're checking this element here, we're checking is nums of index, so is nums of 3 which is 3, is that less than min value of 22? Yes, so min value is going to change to 3. Min index happens to also be 3. Okay, then when index becomes 4, what happens? Is 8 less than 3? No, 8 is not less than 3, so we don't have to do anything. So at this point, we have figured out the min value is 3, and it's at index 3. So now we know we can swap which two elements. So the inner for loop is finished. Swap elements at which indexes? Yeah, and so what variables are they represented as?
Target index and min index.
Yeah. So again, the target index is the one we're currently trying to get the correct value to. And min index is the index of the smallest remaining element in the array. So we want to swap both of them. Okay? So swap elements at target index and min index. So we can use the temp variable that you all had done at the beginning of class. So temp is equal to nums, and we can say nums of target index. And then what do we want nums of target index to be equal to?
Min index.
Yeah, nums of min index. And then what do we want nums of min index to be equal to? Yeah. Okay. Questions on this code? Kind of complicated. I'm hoping the demonstration kind of helped explain the concepts behind it. But to go over the main concepts one more time, the outer for loop is trying to figure out. So the first time when target index is 0, we're trying to figure out what element is going to go in the 0th position. And we check the entire array in the inner for loop to find the smallest value to swap into this target index. Then the next time the outer loop runs, target index is 1. We figure out what the smallest remaining value is in the inner loop. We find it's 3, so we would swap 3 and 54. Yep. Then in the outer loop, target index moves up to 2. So this is the next item in the array we're trying to get the correct value for. We check what the smallest remaining value is. What would the smallest remaining value be? It would be 8, and what index is it at?
4.
So we would swap the element at index 4 with the element at this target index. So the 8 and the 22 would swap. Yep. And then we keep going. Target index is now equal to 3. We're processing this element 54. And we check what's the smallest remaining element. It would be 22. So then we would swap 22 and 54. And then we end up with a sorted array. So again, if I were to put a comment, the outer loop is processing each target index to set the right value. And then the inner loop finds the smallest remaining value so that it can swap the elements. Okay. Any questions here? Okay.
You spell that actually.
Yeah, question.
Wait, explain what the void is for.
Oh, good point. Okay, so normally with functions, when we pass in a value, like with size here, size is like a new variable is created. But with arrays, we can't pass, if we had an array of 1,000 elements, it wouldn't make sense to pass all 1,000 elements from the main function to the our helper function. So essentially all these swaps that we're doing are just happening to one array. And so we don't need to return the array at the end because it's already being processed with these swaps. So yeah, you're going to learn more about pointers and memory in your programming 2 class. Essentially when arrays are passed into a function, you don't have to fully follow this now. When arrays are passed into functions, it's really the memory address here that's being passed. And so then we're directly changing the elements at that memory address. So we don't have to return anything back. Cool. Everyone good with this? Sweet. So for homework, you'll actually be writing the code for selection sort. I would encourage you to watch the video again and really make sure you understand it. I mean, I know you could just come directly to this part and just copy the code directly, but try to step through the explanation again just to really make sure you understand it. Cool. All right. Next sorting algorithm we're going to do is bubble sort. Bubble sort is a little bit easier code-wise to do. So can I get 5 different volunteers for this one? Yep, come on up. Thank you. Yep. And one more. Yep. Okay. Hold up your numbers. Cool. Guess you'll have you on the left here. Okay. So bubble sort is another way. So we're still trying to solve the same problem. These are 2 different algorithms to solve the same problems of sorting numbers. With selection sort, what was the first thing we did here? The one we just learned. We found the smallest, which was 1, and we swapped it to the front. Bubble sort is a little bit different in that it only compares elements next to each other. So in this case, we would check if, so let's say I'm the index variable. So when index is 0, we check if the element at index 0 is greater than the element at index of 0 plus 1. So in this case, is 22 greater than 54? No, so no swap is needed. So now I move up, index is 1, and we check if the element at index 1 is greater than the element at index 2. Is that true or false? That's true, so they're going to swap places. Now index increases to 2, and we check index 2 greater than index 3. The element? Yep, so they swap. Then we do it again, and I check, I'm now index 3 greater than index 4. Yes, so they would swap again. And now I've made one pass. Why do I not check, now I'm at index 4, why do I not check index 4 greater than index 5? Yeah, so normally when we talk about traversing arrays, we go less than size. In this case, I'm going to stop at size minus 1 because we're checking one extra element. Do people follow that nuance? Why we're going to stop at size minus 1? Okay, so now I've made one round, but is the array sorted? No. So now I'm going to have to do another round. So I come back to the front, my index variable gets set to 0, and we check, is index 0 greater than the value at index 1? Yep, so they'll do the swap, right? And then we'll keep working through. It's greater, so they'll swap. 22 greater than 1, they'll swap. 22 greater than 54? No. And then do I even go to this index position? No, because there's nothing we can check after that. So I always stop one short. So now we finished 2 rounds. Now we have to do a third round. And I check 3 greater than 5? No. 5 greater than 1? Yes, so you 2 swap. 5 greater than 22? No. 22 greater than 54? No, and then I don't even have to check the last one. Now I'm going to do a 5th round. 3 greater than 1? Yep, so they swap. And then 3 greater than 5? No. 5 greater than 22? No. 22 greater than 54. Does anyone know how many rounds I would have to do to guarantee that the array is sorted? So now our array is sorted. I had to do 5 rounds in this case. Why do I have to do 5 rounds?
Size of the array.
Size of the array. And if we think about what's the worst case, what's like the worst case for this array? Yeah, essentially like if our smallest value is at the very end of the array, then every round it can only move forward 1. So in this case, because Cameron was at the very end, it took 5 rounds for him to get to the front. So our outer for loop is going to be less than size times for the number of rounds. Cool, so let's write the pseudocode for this one. Thank you guys. Okay, so the pseudocode for this one is a little bit more straightforward. We're essentially saying, let's make this bigger. Okay, so our outer loop was kind of keeping track of the rounds. So for each round, we need to do something. So in each round, we were checking for every element in the array. What were we checking in here? We had like an if statement. Yeah, so essentially if the current element was greater than what? Yeah, If the current element is greater than the next element, then what do we want to do? Swap the elements. Question on this pseudocode. Make sense? Okay, let's see it in code. So we could create a different one, void bubble sort. What are the parameters going to be? Yep, so it accepts an array of nums. If it accepted something else, like you could do it with strings and it would do it alphabetically. In this case, we'll just stick to numbers. And then what else do we need? We need the size of the array. So we know how many rounds to do. Okay. And so in our outer for loop, we can use the variable name round to keep track of how many rounds we're processing. We'll start it at 0. And what do we want it to be less than? So in this example, there were 5. But yeah, we'll do less than size. The size minus 1 will be in the inner for loop. The outer for loop for the number of rounds, that will be less than the size. Because if in the example where Cameron had the lowest value and he was at the very end, like it took him 5 rounds to move all the way up to the front. So that will be less than size, round plus plus. Okay. And in here, we'll have int index equal to 0. And here, what is our condition going to be?
Size? No.
So normally we do it less than size. What is our difference in this problem? Yeah, so it's going to be size minus 1. This is the example where we always got to the 4th person, but we never checked like the very last person because we couldn't check the next element if we're looking at the last element of the array, right? So it has to be less than size minus 1, index plus plus. What does plus plus mean again? Yeah, plus equals 1. That's the same thing as index plus plus is the same thing as saying index plus equals 1. Okay. Which is also the same thing as saying index equals index plus 1. All 3 of those are the same. Okay. So what did we want to do in here? What was our if statement? We want to check if the current element is greater than the next element. So how can we get the current element? Yep. So again, if we want to get an element in an array, hopefully, if you've done Lab 9, today's lecture should be, like this part should be followable. If you haven't done Lab 9, you're probably pretty lost right now. I can't slow down the whole class if you haven't done the assignments on time, right? But if nums of index, so if we want to get an element in the array, we put the array name and then the square brackets. This is also how we get a letter in a string. So for people who did the Wordle project, we said like the name of the string and then the bracket to get the given letter. This is how we get an element. So if nums of index is greater than, how can we get the next element?
Nums index plus 1.
Yeah. So you can do math inside of these square brackets. If index was equal to 3, this would be saying like if nums of 3 is greater than nums of 4. Yep. Okay. Cool. And then in here, what do we want to do? Swap the elements. So we'll create a double temp variable. And what can temp be equal to?
When you put it right under the name of the function because you want it to be a global variable. Is that why? Because sometimes it returns like this hasn't been declared in this scope, and I think it's a local variable.
So this is still going to be a local variable because it's still under the function header. I just put it outside the for loops. Like if we had defined double temp in here, then every time this nested for loop runs, it's going to create a new temp variable and take up more memory. Whereas we really only have to create one temp variable and then just change what it stores each time in the loop. So it's generally dangerous to define your variable inside nested loops because if your loop runs 1,000,000 times, you're going to be taking up 1,000,000 memory locations. So yeah, defining it once before the for loops run. And then what is temp going to be equal to?
Temp is equal to 1 plus 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 1 plus
Not just the index, but we want the element at the index because we're swapping the elements. Yep. So we can do nums of index to get the element. Nums of index, we'll do the swap. So what is this going to be equal to? Yep. Nums of index plus 1. And then nums of index plus 1 is going to be equal to what? Cool. So again, this is why I kind of emphasize so much the swapping, just that hopefully this part makes sense for how it's doing the swap. We're swapping the elements at index and index plus 1. So essentially the current index, the current element and the following element. Yep. Okay, cool. So this code is a lot simpler than selection sort. The concept is a little bit, you wouldn't think of it first. Like when we asked how would you sort the array initially, people said find the smallest value and then move it to the front. That's what selection sort is. Bubble sort, you're only comparing items next to each other. And eventually, after enough rounds, you will end up with a sorted array.
You said selection sort.
Yeah, selection sort is the one we did first. That finds the smallest remaining value in the array and swaps it to the target index. Bubble sort just compares items next to each other. Yeah.
Is there a way we can see like the selection sort in that little AI?
In the visualizer?
Yeah.
Yeah. I won't do it here just because of time, but I think under like useful links and info on the EdStem, I've linked to this visualizer. So you can kind of copy this code over and see it in the visualizer. Yeah. And I would highly encourage people to do so, just so you can see what's happening. Cool. Okay. Any other questions? And again, we don't have to return anything here. We made it a void function because the nums array is already being modified. Okay. Yeah. This if statement?
Yeah, what was that again?
That was checking the current element. So like if the current element is greater than the next element, then swap them. That was kind of when I was walking down the array and I asked like, is this element greater than this one? Yes, swap them. Then I checked the next one. I kept going. Cool. Take a screenshot of that. Again, the bigger thing with algorithms is more the concept. Like you'll have practice coding it, but again, when you code it, it's really, I just want you to get the concept of algorithms. You don't have to like memorize this. As long as you understand what's going on, that's the key here. Okay, so we're gonna finish off with runtime analysis. Does anyone remember what runtime analysis is from Friday's lecture?
How fast your code runs.
Yeah, essentially how quick an algorithm runs. So in this case, both selection sort and bubble sort are solving the same problem. How do we sort an array? But now we want to see which algorithm performs better. So big O notation, that's how we measure runtime efficiency. And it's essentially seeing how efficient an algorithm is in the worst case scenario relative to its input size n. Why are we checking the worst case scenario and not the best case scenario? Yeah, so essentially best case, it's usually always going to be constant time. Like in the best case, we usually don't have to do anything. So it's hard to compare algorithms if we only looked at their best case. Also, if you're a company, you care about your like bottom end of users. So at Google, anytime we make a change, we look at what's called the 99 percentile latency. So for the slowest 1% of users, how fast does our code still run? And is our algorithm good enough? Okay. So I know this is Python code, but it'll help serve the purpose. This first line here, does anyone remember what the big O time is going to be for that?
Constant one.
It's going to be constant time because it doesn't depend on n at all. So the first line is going to be O of 1. These next two lines, this for loop, it's going to print x n times. So what would big O notation of this be? O of n. And then this nested for loop, outer loop runs n times, inner loop runs n times. How many times is this code going to run? It's going to be, yeah, n times n. So O of n squared. So what is our overall runtime going to be? Why is it not O of n squared plus O of n plus O of 1?
You take
you take the largest value. So with big O notation, like if this line ran one time and this n was 1,000,000, it doesn't matter if the code runs 1,000,001 times or 1,000,000 times. They're effectively the same speed. So we say like this big O of n dominates constant time. And you could do the same analysis with O of n squared. Like 1,000,000 times 1,000,000 is way, way, way bigger than just 1,000,000. So we would just say the overall runtime is O of n squared, and we essentially drop the O of n and O of 1 because they're insignificant in this particular problem. Okay? Questions here? Big O notation? If you missed Friday's lecture, I'd rewatch the part where we talk about runtime analysis as the video goes into more detail. Okay, so for our two algorithms here, what would the best case array be? Yeah, but what would it look like?
Like one in which everything is already correctly ordered from these two colors.
Yeah, if everything was already sorted, then we don't have to do anything. And our code would run an O of 1 time. Okay? What would the worst case be? Yes, but specifically,
Reverse.
yeah, essentially if they were like reverse sorted. So in the example, I made sure like Cameron stood at the end because he was holding the lowest value. I essentially like reverse sorted him so that it took 5 full rounds for him to move all the way to the front. Yep. So in this case, we're going to be looking at the worst case. So the runtime of selection sort, again, the code for selection sort looks like this. Oh, did I not take a screenshot of that? Darn. Okay. Selection sort, I think from the morning class I had it here. Okay. So in the worst case, we're going to assume like size is essentially equal to n. If our element had 100 elements in it, size would be equal to 100. So how many times is this outer for loop going to run in terms of n? N times. And then this inner for loop, we're technically starting it at target index, but on average, it's going to run n divided by 2 times. So how many times is the code in here going to run?
50.
What was it?
50 if it's 100.
Close. Like the inner loop, this for loop runs n over 2 times, but it's inside of this loop, which runs n times.
So it's going to be 10 times.
Yeah, this inner loop is going to run n squared over 2. But we can ignore constants, like that's like 1/2 times n squared, but the 1/2 is insignificant. So the runtime of this code would be what? O of n squared. Yeah.
Can you explain why it runs, you said half, the inner loop runs half?
Like half of n because we're starting the target index, like we're starting index at target index. So the first time like target index is starting at 0 and we're checking 5 elements, then we're only checking 4 elements, then 3 elements, then 2 elements, then 1 element. That's like if you do a factorial divided, like a factorial like that, it ends up being like n over 2, but that's like a mathematical trick. Yeah. Okay. Cool. So the runtime of this is going to be O of n squared. If I see this. Okay. Questions on how we got that? Okay. And then if we want to do a similar analysis for bubble sort. So how many times is this outer loop going to run? N times. How many times is this inner loop here going to run? Close. N minus 1. And so then the code inside of here is going to run n times n minus 1. So essentially n squared minus n, but we can drop the n constant essentially because it gets overpowered by the n squared. So what is the runtime of this code going to be? Yeah, it's also going to end up being O of n squared. So selection sort was O of n squared. Bubble sort is also O of n squared. More than just memorizing these runtimes, do people understand how we calculated them? Okay. N is the size of the array.
Always is just
In big O notation, we generally say n is the size. Yeah, the input size. Okay. Do you is there a specific part like so for the bubble sort, essentially we said like size is essentially the same thing as n. If there were 100 elements, if n was equal to 100, this outer for loop is going to run 100 times. And then this inner for loop is going to run 99 times. So the code in here is going to run 100 times 99 times. Just the way nested for loops work. Because it's like this code runs this part in here runs 99 times every time this runs 100 times.
Right.
So 99 times 100 in here.
Okay.
So we could potentially be swapping 100 squared elements.
Okay.
So that's why we would say our runtime. And the reason why we're using n is, in this example I said n is 100, n could have been 1,000,000, n could have been 10 million. We're just generalizing our algorithm to work for any size n.
Oh, all right, I knew that would be on that.
Okay. Other questions?
Is lab today?
What was that?
Is there lab today?
Yep, lab is finishing up the 2D arrays lab. So if you came on Wednesday or Friday, you're good. If you haven't come into lab, make sure you come in today. We also have the homework party today from 3 to 5. I think the past couple weeks, students have mostly been able to finish their homework in those 2 hours. So if you haven't done homework 9 yet, make sure you come in. And then most critical lecture remaining this semester is this Wednesday's lecture. Because this Wednesday, 2 days from now, we're going to be going over the final project. We're going to be playing the game in class. We're going to show you how to get started. So really, really, really try to make sure you come into class on Wednesday on time so that you have a solid foundation for the final project. Yep. Cool. And don't forget to vote in the conference room, most likely. Yep.